I guess this ran a bit faster on my machine, but it shows plane on box, box on box, sphere on box, and sphere on plane, and sphere collisions, which is really nice. We had this in basic particles. Some of the boxes are bouncier than others, just see them like launch out into the distance. But yeah, this is essentially the basics of the book implementation. After finishing all the sphere collisions, I started with the box collisions. Box on plane was pretty simple. It made a lot of sense to me. You know, if a single vector is below the plane, then obviously the box is intersecting with the plane. So you have your two boxes. You get the center-to-center distance, and then these check overlap functions will check the different sets of axes that we were talking about. If it becomes, if it's anywhere between these checks, you know, you have a vertex to face collision. In here, it's a vertex face collision, except with box 1 and box 2 swapped. And then any of these here would be edge-edge collisions. Those are the only two different types of collisions you can have with a box on box that would at least matter. As the book described, there's the different levels of collisions and how the vertex, and vertex face, and edge-edge, and how they all have different priorities. So it works through the highest priorities, and if it finds one of those first, it'll use that and ignore the other ones because it wouldn't matter.
But when the joints are on, it's kind of jumpy. I spent longer than I would have liked to try to fix it. I put little things that made it slightly better or made it hold together longer before the body explodes. It's enough. So, body's kind of jumpy. And then it just falls apart and explodes. Less joints. I think what the issue is that there's like the 4 joints or so that are connecting to them are pointing in so many different directions that it's penetrating in one way or another to the point where it just decides to shoot off in one direction. So it was testing with like just the arm, and then the arm had gravity and would slowly pull it down against like the explosions. But you can kind of see how they will act nicely. There's only like a few. I guess that guy's getting caught. Oh, yeah, they also fight with each other.
Also has a chain in it. The thing on the left side is a chain that expands and contracts. The ropes have set lengths, and this one that swings around, it has angular momentum. These two, they come down and they hit, and then they sort of spin around a little. That's the rope. I've got a falling object simulator. This all combines the earlier simulator code that I wrote for my initial physics engine, because I really liked how it allowed me to like make new scenes and modify scenes and switch between scenes, so I could like on the fly within 30 seconds create like a whole new test sandbox to start putting stuff in.
The coolest thing about this is that being the Unity fan that I am, I built my entire architecture similar to Unity, with everything being components. If they get stuck in a collision box with the same self, it freaks out. See those two freaking out together? Yeah. It's because when I do my collision detection, what I did is I said, okay, go in the direction you're supposed to go one step ahead, but I didn't tell it to like bolt one step ahead. I just said just one small update, just so I can correct it. But it's not enough to correct a like overlap entirely. But yeah. Anyway, those are the bugs.
Really crappy stretched out grass texture on the bottom. If you actually use the pixel shader and vertex shader effect, it's all really in the pixel shader, but I have to use the vertex shader to get some information. It kind of places it around, and if you look at the tiles right there with the yellow circles, it's actually kind of showing a different visual representation rather than just seeing all the grass, because you can't really tell what's going on with the grass. It just looks like grass. So it kind of is randomly dividing it up, and you can see how there's like different squares. And some of them, there's actually, you can't really see it there, but there are some that are like really tiny and really like thin and long, and others that are like actual squares.
Let's pretend for a second that this is some kind of first-person, third-person game, and that little green square there in the middle is your character and where you are. And that's where the camera would be if you were playing the game, but this is just a representation of the map from outside. So What we've got here is a height map, which is a representation of a terrain and how high each portion of the terrain is. Okay, so say this is our terrain. Once we enter the actual game mode where it's being rendered, I have the screen separated into 9 different sections, and you can see the one that the player in is at the highest level of detail, and it'll be drawing for pretty much every single piece of data in the height map, a polygon around it, and sections that are farther away will be drawn less detailed. So if you move to one of the other corners, it'll draw like those really far ones in the absolute lowest level of detail, the ones that are semi-close and medium level of detail, and the only box that it's actually in is drawn at the highest level of detail. So
we're going to play the guessing game of, is this the compressed texture or is it not? Like, can you tell if I change them? Let's see. Can you tell a difference at this distance? No. This distance? Yep. Nothing? Ooh. You have to get really close, which is the cool thing. You can see a slight blurring if you get really close. Now you can see it. And anybody want to guess how much bigger the compressed texture is? It's about 8 times bigger.
You can see the light source is the orb, and the boxes are translucent. There's right here, in this first set of boxes, there's 3 different kinds of boxes. There's some that are not translucent at all, and then there's 2 different colors of translucent boxes. So if I move the light source closer to the boxes, you can see as the light gets closer, they glow more, and they glow depending upon their thickness. So the thick boxes at the bottom glow less than the thinner ones at the top, and if the light gets really close, you can see there's a real difference between the glow. So I pull the light source all the way back away, and then bring it back closer. You can see different proximity and based on thickness. Here's the pixel shader, and you can see on the color RGB it takes in the object's texture, and it takes in the light's color, and it modifies the pixel by that amount.
For my project, I did dynamic fractal terrain. Fractal terrain is an algorithm used to generate semi-realistic bump maps on terrain.